Well, hello, everyone. Welcome to our Learn Live session, Model and Partition Your Data for Azure Cosmos DB. I'm one of your hosts, Mark Brown, and I have with me today
Gary Hope. I'm also part of the Cosmos DB team. I'm very happy to be here today with you guys.
Yeah. How you doing today, Gary?
All very good.
Yeah, I'm excited. I think we're among the first slate of sessions, or at least breakout sessions, for Ignite this year. So what better way to get started than to talk about Cosmos DB and learn a really important topic on modeling and partitioning data.
Very exciting to be kicking off today. So in today's session, we're going to be walking you through the Azure Cosmos DB modeling and partitioning module of our new learning path. And hopefully after today's walkthrough, you'll be super fired up to go and do this on your own. Besides today's session, walking through on your own afterwards is going to allow you to reinforce some of the stuff that you've learned here today, experiment with the data that we provide in this module, and give you some real hands-on experience of how Cosmos DB works and how the data within Cosmos DB works. So today's session is live. All the mistakes we make are our own. What we're going to cover today is really around the access patterns, how you understand your application's access patterns, and how you model your data according to those access patterns so that you get a highly efficient, highly scalable Cosmos DB deployment at the end of it. So remember, as I said, today's session's live. Head over to the chat, say hi. We have got a couple of moderators in there. Deborah and Govind are over in the chat. They'll be supporting you with the answers to your questions during the session for those that we can't take live. Thanks, Deborah and Govind. And with that, Mark, let's dive right in. Over to you.
Sounds great. All right, so let's dive into the scenario that we've got here. You're working for an e-commerce startup. We'll call them Contoso Mart. How's that sound? I just made that up. And in this e-commerce company, you're going to work on building a proposal for designing an efficient database design for their e-commerce application. And you've been given this relational model here to start with. So let's go through each of these entities. So we've got a customer table here, and that's got some name and email address, phone number, and then a one-to-many relationship to another table called customer address, where you would have multiple addresses that you would ship to, maybe billing address, that sort of thing. You've also got one other customer table, that's customer password, and that has a one-to-one relationship with the customer table there. Next up, we've got our product tables. So we've got a product table, and that is related to a product category table. So there's a one-to-many relationship between product category and then products, right? Because you've got multiple products for every product category. You've also got product tag, and that has a one-to-many relationship to a product tags table, which has a many-to-many relationship to product table, because you can have multiple tags per product and multiple products per tag. And then lastly, we've got our sales order table. So we'll have a sales order table here, which is the sales order ID and a customer ID. And then you have the sales order detail. That's going to hold all of the items for your shopping cart when you purchase that order. So you'll have a sales order ID, a SKU, a name, a price, a quantity, etc.
Your typical e-commerce schema.
Kind of your typical. And in fact, if this looks familiar to you, maybe you are familiar with the AdventureWorks 2017 database. This is, in fact, a subset of that database. And a good place to start, since most people are familiar with that whole application. All right, so let's go through what are we going to be doing in today's session. First, we're going to take that existing relational database, that existing relational model, and we're going to redesign it for Cosmos DB. We're going to make it efficient, scalable for a distributed NoSQL database like Cosmos. During the session, we're going to learn the differences between a relational database and a NoSQL database like Cosmos. We're also going to understand how to use access patterns to model data. In a relational database, it's often the relationships of the entities that's most important to understand when you're modeling data. For a NoSQL database, this isn't the case, and we'll get into why as we go through the session. We'll talk about concepts like when to embed data versus when to reference data, Cosmos being a JSON data store, you can store hierarchical data and embed data within other documents. We'll also talk at quite some length about choosing a partition key. And this is probably one of the most important things you're going to decide when you're designing a database, because it's ultimately is what's going to allow you to scale that database so that you can get high efficiency and scale up and down. And then lastly, we're going to cover some concepts on how to model lookup or reference data in an application, like our product category or our product tag data. That would be kind of reference or lookup data. So we'll describe and walk through how we're going to model that kind of data. All right, Gary. So we've got some exercises we want to show these folks. So you want to walk them through getting set up for that?
Yep. So we're going to do a quick setup here to show you what you need to do to get going. This is the module, and if you come down working through the introduction, which we'll talk you through now, you're going to get to the exercise piece. And once you've clicked on that exercise piece, it'll allow you to set up an environment. There'll be a prompt here for you to activate your sandbox, and that'll bring up your sandbox. And you'll see in many of the learning paths that you go through today, if you go through others, this experience is fairly similar. If we go and run this, what it's going to do is it's going to set up a bunch of data for us inside our sandbox here, so that we can run the demonstrations against that data when we've got it all running. Once this is set up, we're going to head over to the portal, and within the portal, you'll discover that there's already a provisioned subscription for you, and within that subscription, there'll be a resource group, and within that resource group, what you'll eventually see is all of the resources that you will need to do that. While this does that, while this builds out, we'll continue and introduce you to all of the content.
Perfect. All right. So let's talk about, well, let's start at least about understanding the difference between a relational database, like say a SQL Server, a Postgres, or a MySQL, versus a database like Cosmos DB. In general, databases like Cosmos DB as a distributed NoSQL database are characterized by being both horizontally scalable and non-relational. So relational databases will typically, hey, Gary, you want to advance it? There we go. One more. And there we go. And we're live, folks. So typically, relational databases will grow by increasing the size of the VM or the compute they're hosted on. NoSQL databases are fundamentally different in that they scale by adding more servers, not increasing the size of the server. Now, in Cosmos, we call these different servers partitions, and they're there to store increasing amounts of data. So as you add more data to a database like Cosmos, we'll continually add more physical partitions or servers behind the scenes so that we can store that data and access it. Now, you need to be able to get to that data and do so efficiently. So within these partitions, we have defined what is called a partition key. And you define this when you create your container within Cosmos, which is itself a logical kind of grouping of all of these different partitions for your data. So the partition key is used to help kind of efficiently route your request to go find the data. You can look at it as kind of like an address to like a building so that you know where the building is located. You can go and find it quickly, get your data, and then get back out again. Now, this may appear or seem to be kind of constraining in terms of a database to have to define and use this partition key when accessing your data, but it does have some enormous benefits. One of the things that you're limited by with a relational database is that unsharded relational databases can typically only grow to be about 4 terabytes in size. A NoSQL database like Cosmos can grow to an unlimited size. The amount of storage you can contain is pretty much infinite within there. The other really interesting thing about a database like this is that no matter if the database is a megabyte in size or a petabyte in size, you're going to be able to get your data with 0 change in the response times. This is unlike any kind of database, at least a relational database, where you could have a megabyte of data or a petabyte of data, but you're still going to be able to access your data with single-digit latency like Cosmos DB can provide. So next is kind of the difference between these two databases is Cosmos DB is non-relational. So what I mean by that is that there's no foreign keys or constraints or any kind of joins or anything like that that's enforced at the database level. And the reason is because we are a distributed horizontally scalable database, and we store data on these different physical servers. So while you technically could put locks on data when you're trying to access it and provide kind of those ACID guarantees on the data, doing so could cause issues with availability and also latency on your data. And databases like Cosmos are designed to be highly efficient, highly performant. And so that kind of takes precedence over how we would design a database like this, and why you don't see these types of relational constraints on a database like Cosmos, or in general on distributed NoSQL databases in general, because they're really designed for that high efficiency, low latency type of scenario.
Makes sense.
So last is understanding. I want to explain kind of the difference between the databases and the design goals between these things. Relational databases has been with us since the 1970s. In fact, I think 1970 is when they first appeared. And back in those days, the cost of storage relative to compute was rather high. As a result, kind of the objective with normalizing databases, or normalization in the first place, is to reduce the duplication of data. They were trying to optimize for the storage in that sense. Now, fast forward 50 years, the world has changed. Compute relative to storage is now the most expensive thing. I have a cell phone here with about 1 terabyte of storage on it, and this thing only cost me a few $100. Back in 1970, I probably would have spent millions of dollars if I could even have gotten 1 terabyte of data to use for my database. So in that sense, the compute now is expensive relative to storage. And now what you find is with a NoSQL database like Cosmos or others, you want to optimize around the compute. And what that means is you want to optimize around the request. And so when you're modeling your data for a database like Cosmos, this is one of the things we're going to look at, is how do we reduce the usage of compute to satisfy our request. And so we'll spend the rest of this session talking about that and show you the patterns on how you do that.
So a lot of people are probably wondering at this point, can you use an NoSQL database to deal with data that has these relationships? Don't all applications have relational data and relationships between the entities they're working on? And absolutely, the answer is yes. NoSQL databases absolutely can be used for this part of the problem. They're different from traditional relational databases in that they're often targeted for those scenarios where we want to meet or exceed the performance requirements of that relational database. What are the availability considerations? The other reason to use it is that developers are really wanting to take advantage of that flexible, no schema flexibility that comes with non-relational databases as well. Techniques for building these databases and the models that you model the data with are different from that relational model. They're not always intuitive, and especially for people like me, where we come from a relational background, some of the best practices for NoSQL databases are actually anti-patterns when you think about it from a relational perspective, and vice versa. So the best practices for building relational databases don't translate well, and that's a very important concept to carry through. Don't take any of those relational modeling concepts and apply them directly to your NoSQL databases.
Yeah, it's often we see where customers don't even, I mean, nobody reads the manual, right, or the docs, but you literally do not take relational thinking into designing this type of database. It's just it's not gonna end well.
Absolutely. So for the remainder of this module, we'll be discussing that in detail, and we'll talk you through all of the different considerations you need to have between the relational and the non-relational world as we take this relational model into the non-relational world. We'll go through this step by step, and we'll demonstrate you practically with the sample data that we've got how to do that and create a high-performance, cost-effective Cosmos DB deployment at the end. With that, it's time for our first knowledge check, Mark. Is everyone ready?
I am ready.
Cool.
Hit me with it.
So here's the first question. So what is the maximum size of a NoSQL database? Let's be specific. What's the maximum size of a Cosmos DB database? I'd say 100 gigs is relatively small. There's lots of small Cosmos DB databases out there, but what we're asking for is what's the maximum? Yeah, 100 gigs is probably even small for a relational database today, right?
Yeah, well, it's less storage than I got on my phone.
Absolutely.
How about 4 terabytes? That's pretty good size. And I think I remember something about 4 terabytes earlier when I was talking.
You did mention 4 terabytes earlier.
Yeah, but that's still not very big. Maybe, how about 100 terabytes? Now we're getting into some good size.
100 terabytes is getting pretty big. But the advantage of a NoSQL database is really that we have this infinite scale. There's no limit to how much data you can store in Cosmos DB, and it will grow with you as your data grows.
Well,
second question up. What do we do to optimize? What do we optimize when reading and writing data to NoSQL databases?
Well, okay, we got some answers here. So we got storage efficiency, but I pretty clearly remember talking earlier that we're not trying to optimize for storage here.
Storage is getting really cheap these days.
It is cheap, right? And network efficiency, I mean, all of these databases run over a WAN in the cloud. So it seems like optimizing for network bandwidth and payloads, that would be a good objective for designing. But maybe there's another one that's even better. What do you think? Maybe...
So, like compute is the only one that we've got left there.
Yeah.
And compute is the thing that's really expensive today, and it's the thing we want to optimize for in Cosmos DB or in any NoSQL database as we design the schema and the partitioning strategy.
And if you're optimizing for compute, you are, as a side effect, probably going to optimize for network as well, because you're going to reduce the number of requests typically that you're going to make on the database.
Absolutely.
Yep.
So let's talk about these access patterns. I mentioned earlier when we introduced ourselves that we're going to be talking about the access patterns and why that's important. The objective when modeling your data is to ensure that the number of operations that you do is executed in the fewest number of requests and at the lowest cost in terms of request units. In Cosmos DB, we measure the cost of an operation in terms of request units. To do this, you need to understand the relationships between the data and how they're accessed. The access patterns are important because they, along with those relationships, define the cost of the operation and how many of those operations you'll need to do a specific business operation. So let's start with a little bit of detail around our customer model again. So here we have our customer. It has an ID, a title, a first name, a last name, and some additional details associated with that customer. And it has a one-to-many relationship to customer address. It also has a one-to-one relationship to the password associated with that customer. In our application, we also have a bunch of operations that relate to that. We create a customer when the user signs up for the first time. They're going to provide us with their profile information. They're going to enter their addresses of where they want the goods shipped to, where they reside, what is their billing address. We're going to also provide them with the ability to update that information throughout the application lifecycle. And they're going to want to be able to retrieve that information every time they log in. We're also likely going to want to bring all of that data back together. We're not going to want to bring the customer back independently of their address and independently of their password. When the user logs in, we're going to want to validate their password at the same time we've validated that they exist. And we're going to want to load up those addresses so we know where to ship the goods and how to calculate the shipping costs. So for each of these operations, we're going to perform that together. When we think about this from a NoSQL perspective, Cosmos DB provides you with the flexibility to model your data in this JSON format. And that provides us with a lot of flexibility. If we have customers as the starting point, so we start with our customer as the base of our model, we can model that one-to-many relationship to customer addresses by embedding it as an array. So over here, we can actually embed that customer address as an array for each of those addresses. We can also embed the customer password in as an embedded JSON object in our customer object as well. Now we have a single document that represents everything related to the customer, and we can perform operations against that consistently in single operations.
Great. So as Gary mentioned, he's embedding data inside the customer entity there, right? And as I mentioned earlier, Cosmos DB is a JSON store. So you can store hierarchical data within a single document within there. Now, excuse me. There are some rules for when you want to embed versus when you want to reference. You can't always embed data within a single document. And those rules are pretty straightforward. So let me kind of go through them. First is when you have a one-to-one relationship for data, like say customer and customer password, that's a good candidate for embedding that data inside the same document. Another kind of scenario would be what we call one-to-few. Now, one-to-few may sound weird if you're a relational developer. You may be wondering, what does that mean? It's essentially a one-to-many relationship, but the relationship is bounded. An example of this would be our customer address data, where we've got customer record and just a handful of addresses. You're typically not going to have hundreds or thousands of addresses that you're going to ship to, unless you're a generous fellow, maybe. So in that one-to-few relationship, we can store that bounded array of data. And in this case, it's going to be addresses. And then the last scenario is when that data is read or updated together. And again, our customer data fits the bill precisely here, because we're going to want to access all of that customer data all in a single shot. Also, updating the data is also important because you want to avoid where you have asymmetric access patterns to data. Let's say you have a document, maybe it's rather large in size, and you frequently update a small number of properties on there. This would be a good candidate for shredding that document and putting that into separate documents, because the cost of doing the updates on a small number of properties for a very large document can be rather high. Now let's go into when to reference data, because it really kind of ties into that. For scenarios on when you want to reference data, it's when you have that one-to-many relationship, particularly when that relationship is unbounded. Classic scenario would be if I'm creating like a blog platform and I have a document that contains my post. I would not want to embed comments inside that post document. Maybe I could fit most of them in there, but the problem is that if the comments grow too large, I'm going to break the maximum document size for Cosmos, which is 2 megabytes. The other problem too is that if I'm continually adding more data to that document, it's growing increasingly larger. The cost of doing that update and the latency for doing that is going to get higher and higher. The other scenario too is if you have a many-to-many relationship with your data. One of those scenarios we're going to demonstrate here in a little bit when we model our product tags data. So we'll show you why you want to model that as a many-to-many relationship within Cosmos. And then finally, if the data is read or updated independently, much like I talked before, this is a good candidate for where you want to reference data. So if you had a document where you had this asymmetric update pattern, this is one where you'd want to shred the document, and you'd want to have one document that's potentially smaller with data that you update frequently, and then another document that has largely static data that you don't update that frequently. This is much more efficient in terms of how you would want to model data in a database like Cosmos. Yeah, Gary, do you have something you want to say?
So in our example, if the customer wanted to update their password independently of the entire customer record, we might want to do that in that sort of scenario as well.
Yeah, except that how often are you updating your password?
Yeah, no, exactly.
You wouldn't.
But you might want to validate it multiple times. There'll be those scenarios where you want to do these operations separately and keep those parts of those documents separate.
You know, and that's kind of a key to understanding and analyzing access patterns, is understanding the cost of those operations and the concurrency with which they happen. If it's an expensive operation but does not happen frequently, then maybe it's not a big deal, right? But if it's a high concurrency operation and it costs a lot, that's something to take a closer look at.
Absolutely.
Yep.
So we're back to our knowledge checks here, Mark.
Awesome. All right, hold on. I'm told I've got to update my teleprompter here. So let me refresh that. Okay, let's go with a question here. So for a NoSQL database, how should unbounded one-to-many relationships be modeled? What say you, Gary?
So let's think about this. We've got a couple of options here. We can save them as separate documents and reference them, or we could store them in separate containers, or we could embed them in the same document. Now, they specifically say unbounded one-to-many relationships. And you mentioned earlier there's a big difference between bounded and unbounded and how we model some of those things.
That's
so if we save them in a separate document and reference them, That's one approach, but that sounds rather relational to me.
Oh, you think so? Huh. Well, for unbounded, storing them in separate containers is the one that sounds the most relational to me.
That you're kind of mapping tables to containers.
Yeah, that doesn't work at all. Embedding in the same document, well, that doesn't sound good either, because if it's unbounded,
that limit, right?
Yeah, you're going to blow up the 2 megabyte limit.
Yep.
I do think.
So even though it sounds like a bit of a relational thing where you save the separate documents and you reference them, that is going to be our best solution for these unbounded relationships.
Yeah, I think so too.
So how does embedding data into the same document affect performance and cost?
Well, let's see. We've got 3 options here. Increase latency and lower cost. That doesn't make sense to me, Gary. How could you have something that increased latency and lowered cost?
Yeah, that doesn't sound right.
Yeah. Lower latency. Well, that sounds potentially correct. But I think that the right answer here is going to be both reduced latency and cost.
I agree. It will be reduced latency and cost associated with that.
Yeah.
So time for an exercise again, Mark.
Awesome. How's your setup going?
Sorry?
How's your setup going?
My setup going, yeah. We forgot to kick off the data load while we were waiting for the initial script to run. So it's still busy running, but I think we've got enough data here to do some demos.
Okay.
So we need to set up the environment. We've stepped through that step by step already. We're going to measure the performance of storing data in the separate entities, performing operations against them separately, specifically queries. And we're going to add up those costs and see how that compares with doing a single operation with an embedded data model where we've modeled all the data together, exactly like we've just stepped through here. So let's head over to our subscription again. If we head over to this resource group, we should now let's do a refresh here. We should now see that we've got some additional resources. And here's our Cosmos DB account. Within that account, we have some data deployed. And if we have a look at what that data looks like, here you can see our original data model that we started with. Here we have customer, and within customer, we have customers modeled separately. This is just the customer detail, their first name, their address, all of those details that we expected. Here
so this
we
is
have
going to
modeled
be the naive model, right? We
the
just
naive
basically
model, just like you would model them in a separate table in a relational world.
Yeah, right.
So here we have the customer address also as a separate object here, and we have the customer password. So this you can see here's the hash and their salt.
Yep.
So let's have a look at running a couple of queries against this data. We'll start by querying the customer. Let's pull that back first. So let's run a query against this. So here we have a query. This is a specific customer. And I'm going to bring back all the data related to that customer from this customer container. We can close this for the moment. And what we can see here is that you've got a single document coming back. If we have a look at the query stats, Cosmos DB tells you how much each of those operations cost. So here we've got 2.83 request units that it cost me to perform that query. Let's go back and do a similar thing for our customer address. Now, in the customer address, we've got the ID of the address because we have multiple addresses, but we also have this customer ID here. So let's run a query, and let's query for that customer ID where it's the same as that customer that we had before. So now we're looking for all of the addresses for this customer that's in this container. And here you can see also a single customer record. They only have one address. And if we have a look at that cost, it's also 2.83 request units. And lastly, we need to do the same thing for the customer email. So, I mean, password, sorry. So let's do a query that's going to pull back this data And this one is modeled, again, the ID of the document is the same as the customer ID, so we'll be able to bring this back. And if we have a look at this, in query stats, what we have is 2.83. So we've had 3 operations. They each cost us 2.83 request units. So my math is not great to do that in my head. We can know it's about 9, but let's have a look exactly how much that cost us. So there's 8.49 request units. So those 3 operations, and all they did was bring back the customer details to our application, cost us that amount. Let's have a look now at our database number 2. And in this database, we've got customer again, but within customer, we have both the customer and the details mapped into that customer. So here we can see we've got our first name and last name, but within that same document, I've got the address of the customer. Let's send this away. The address of the customer, and you can see the password there as well. So we've modeled this exactly the same way we've been talking about. If we have a look at this, so let's run a query for this, and let's bring back this customer detail. I run this query. Now it's a single operation, so firstly I don't have to wait for the one operation to finish before running the other one. So the latency overall is going to be lower. But if we have a look here, we've got all our customer details coming back, exactly like we had in the document. And our total is now 2.83 for the total. So this is significantly cheaper to do than run each of those operations independently.
Yeah, I mean, you basically are saving, what, 66% of your throughput by embedding it, and you've done it in a single round trip. So that's also going to be more efficient, right?
One round trip, much, much more efficient.
Yeah, exactly.
So we went through these steps. We ran the queries for the individual ones. We combined the cost for that. We compared that to the cost of a single operation. And as we observed, much cheaper to do it that way around.
Yep.
Let's talk a little bit about choosing this partition key. You mentioned up front, Mark, that this was an important part of our design process, is choosing the partition key.
It is. Now, you remember earlier I said Cosmos DB stores data in containers, and these containers are functionally like a logical wrapper around these partitions, which is where we physically store the data. And that to access this data, you need to have what's called a partition key, which is what we use to assign data to go to each of these different partitions. Now, this partition key is functionally, it's a property on each document, and it's a required property on these documents. And so data within the same logical partition is always located, documents with the same partition key value are always located on the same logical partition. Now,
so let's take a step back. Let's go and say, let's have a look at this. Cosmos DB is horizontally scalable, right? Yep. So if these are our physical partitions, as we scale out, we're going to add more physical partitions.
That's correct.
How does it know where to store your data? And that's really what we're doing when we're providing it with that.
That's right. That's the partition key.
So for each of these physical partitions, we have some constraints. A physical partition can have 50 gigs of data and a maximum of 10,000 request units. So think of that as that's the maximum amount of resources that this node can provide. We abstract away this physical implementation in Cosmos DB with the introduction of a logical partition. And these logical partitions provide a uniform way to group data together and distribute them across all of these physical resources. It allows us to store data on a node predictably so that we can get to that data easily. Each of these logical partitions that we now have that reside within physical partitions have a maximum size of 20 gig. So those are the constraints that we have when we're designing our database. The partition key itself provides us the ability to route that data onto those logical partitions in a predictable way. So we use the partition key property, and it can be any property within your document as long as it's consistent across all of your documents. It defines the route on how you get that data to a specific logical container. You define the partition key when you create the container, so it's a one-time operation. When you create the container, you choose the property that's going to be your partition key. And then when you model your data, you're going to want to do it in such a way that it distributes all of the data across all of the nodes in your environment. So each physical node will have a set of logical, each physical partition will have a set of logical partitions within them. And we want to spread our data evenly across all of those logical partitions. This is especially true as your data grows. So when you start getting into physical partitions, data needs to reside on these separate physical partitions, and we need to know how to route that correctly. The other thing to realize is that these, the impact of choosing this partition key only surfaces itself from a performance perspective. And if you don't do testing under load or with the workload pattern you're expecting when you're developing your app, you're not going to see the impact of that while building your app. If we partition data correctly, it will be well distributed both in terms of storage as well as throughput. And you will avoid what we call hot partitions. Hot partitions occur when all of the data ends up on one logical partition or one physical node or physical partition because we've chosen a partition key that doesn't allow us to distribute that data evenly. If I end up with a scenario like this, where I have all the data residing on a single physical partition, I'm going to run into the limits of that physical partition. So I want to choose a partition key that has high enough cardinality to distribute the data out evenly across all of those nodes because it uses that partition key to distribute it correctly. So let's think of this scenario. If each of these letters here represent a tenant, and I have 6 tenants in my application, you'll see that B, C, E, and F have a small number of documents associated with them. Tenant D has a fair amount of documents associated with it, but tenant A was that first tenant that we had, and it's grown massive. It's likely to run up against that 20 gig limit for that logical partition. So in this scenario, what I would want to do is use something with a higher cardinality than the 6 values I have for tenant ID to distribute all of these documents evenly across my partitions. In the case of throughput, we can also suffer from a hot partition. And that's where all operations or a majority of the operations associated with the way I'm accessing the data land up on a single logical partition at a specific moment in time. And this creates a scenario where this partition is doing all of the work and all of these other partitions are wasting the resources that you've got provided. So let's think about it. If I provisioned 30,000 request units across these 3 physical partitions, Cosmos DB is going to divide those resources out evenly across this environment. And I'm going to end up with 10,000 request units per second across each of these physical partitions. That means that any operation that is associated with just a subset of these logical partitions will only be able to use the 10,000 request units that's allocated to that physical partition. So in essence, we want to choose a scenario that spreads the request units out evenly and utilizes storage in a distributed way that is evenly distributed across all of that data. And those 2 things, when I think of them together, will allow me to design a database that is highly scalable and highly performant. There's another consideration that we need to have as well, and that's whether your workload is read-heavy or write-heavy. In a write-heavy scenario, I'm going to want to absorb as much of those requests evenly across all of the physical partitions that I've provisioned. And in order to do that, I'm going to want to choose a partition key that is going to spread those writes out in an even way at any moment in time. Remember, Cosmos DB's provision throughput is requests per second. And in a request per second scenario, it's that moment in time throughput that we need to be worried about. If I have a read-heavy workload, we're going to want to ensure that the queries land up on a single partition and you leverage the resources from that single partition, because fanning out that query will hit each of the partitions in my cluster, and that way it'll distribute all of that that query workload across all of those physical partitions. Each physical partition will have some cost of processing that query, and together they will cost more. It'll add up as I start adding physical partitions to my cluster. So let's have a look at this example. I have a query here where select star from my collection where username equals Mark, and we're partitioned on username. That'll allow this query to go to a specific partition and execute just within this partition. If I ran this other query against this exact same cluster, what you're going to end up with is a scenario where I'm searching for favorite color and I'm looking for orange, but it is not on the partition key. And in this scenario, every one of these physical partitions needs to participate in that query to give me a result. And that becomes more expensive, as I mentioned, especially when I grow my cluster. And those cross-partition queries, that's what we call it when they run across multiple partitions. Those cross-partition queries can become expensive as that cluster grows. The important thing to remember, though, is that you always have a mix of both. It's never a one or the other scenario. You always have a mix between queries that can be directly accessing your data and those cross-partition queries. You really just want to make sure the majority of your queries are optimized and are single partition queries.
Hey, Gary, we got a question from one of our viewers here. What happens when a physical partition is about to exceed the limit of 50 gigabytes? From Vikram. Two-part question. Also, what happens when the same happens for logical partition when the limit exceeds 20? So as we approach the 50 gig, remember that that 50 gig consists of multiple logical partitions that live within that physical partition. So as we approach that 50 gig, what we will do is we will split that physical partition so that you end up with some of those logical partitions living on a new partition and the remainder living on another partition. And that way we can continue to grow the database as we approach those limits associated with the physical partition. Yep.
In the case of the logical partition, though, it's a little bit more challenging because that logical partition is how we're routing the data. It's the partition key that defines how we route the data to that logical partition. And in that scenario, you're going to end up with a hard limit. When you hit the limit of your 20 gig associated with your logical partition and you try add the next record, you're actually going to get an error back in your application.
Yep. That's why it's so important to choose a good partition key that is not going to end up with the storage, a hot partition on your storage.
Absolutely.
Yep. All right, so let's keep going. We're
now that we've gone through all of this theory, we've actually got some practical understanding here now. Let's map that back to our scenario. We've got those three operations that happen, right? We've got a create customer, an update customer, a retrieve customer, and we perform all of those operations associated with the customer. You saw that I included that GUID in there, and that GUID is the thing that I'm going to use to look up that customer information. So choosing that GUID, that ID, the customer ID, as my partition key makes a lot of sense. That means that every document is effectively going to have its own logical partition. I'm not going to have to worry about that 20 gig limit, but you may now be worrying, like, is there going to be a problem with having each document having its own logical partition? Maybe I have millions of customers. Are we going to have millions of logical partitions? And are those millions of logical partitions going to cost me anything or be a problem for me? And the answer is no. It's perfectly fine to have as many logical partitions as you want. Those logical partitions are virtual things. They're not physical things. All the data lives within that physical partition. And Cosmos DB will automatically redistribute those logical partitions across physical partitions as your cluster grows.
Right on.
So, Mark, you mentioned something about point operations right in the beginning. I demonstrated a few queries, and those queries were going in, accessing a single document in some cases, but it was using the query interface to get those documents.
That's right.
What are these point operations you were talking about?
So point operations are where you bypass the query engine and go directly to our backend storage. And in this scenario here, where you've got data that's modeled that has an ID and a partition key that's the same. That's functionally a key value store, and you can use point operations to get at that data. So let's get my screen up here. I'm going to show you guys something cool here, and that is how do you do a point operation. So I'm in the Cloud Shell here that you get when you start the sandbox, and I'm going to show you something cool, little hidden stuff in there that you wouldn't see because it's not in the exercise for this module, but it's actually, there's a lot of code that we have inside this GitHub repo that you're going to do a clone on when you set up the lab. So let me show you. Here's one of the projects.
We could spend a lot of time exploring what's in this Git repo. I think today we're super short on time, so
yeah, we're gonna
keep it to the point operation.
I'm gonna go as fast as I can here. So I'm gonna go to a function here that's called get customer, and I'm gonna get a reference to my database, a reference to my container, and I'm gonna get this string ID that's the same customer ID that Gary showed in his query earlier. Now I'm gonna call this function called read item async. And I'm going to deserialize this into our customer object. It's the V2 for the V2 database in there. Now, read item async takes two different things. It takes the ID for the record, and that's the customer ID. And then it takes a partition key. And that, of course, is also the customer ID. So I'm going to run this operation, and then we'll spit out the request charge and show you how cool it is to use these types of operations. So I'm going to .NET run my app. Here we go. I've got my little app running here. Now I'm going to run option O here. And here you can see we got query for a single customer. This is what Gary showed earlier, right? And the request charge is 2.83. That's cool. Let me show you this. A point read for a single customer. Boom. Boy, that was fast. 1 RU, right? So cheaper still and faster because it's not going through the query engine. It's going directly to the backend storage within there.
And we guarantee the latency of those queries for those point operations.
That's correct.
Yeah.
If you're going direct mode through our SDKs, so .NET and Java SDK, I believe, are the two that support direct mode. Those operations for 1 kilobyte of data or less are always guaranteed to be less than 10 milliseconds at P99. So guaranteed latency SLA for Cosmos, which I think is what Scott Guthrie mentioned earlier, didn't he?
I believe so, yes.
Yes. Okay, back over to you, Gary.
So we're back to questions. Our next question is, when data is not partitioned correctly, where can hot partitions occur?
Well, let's see. Storage, potentially. Yeah, I think you talked about storage with your example there. And then
we end up with too many documents all living within a single logical partition.
Yeah, and then also you could have it where all the requests are going to the same logical partition as well. So I think your right answer here is going to be, that's both. Right. B.
Well, you need to think about both as you choose that partition key. You don't just want a scenario that solves for distributing your data evenly across all of your logical partitions or distributing your requests evenly across all of your partitions. You need to factor in both.
That's right. How about this question? When designing for write-heavy workloads, how should writes be distributed?
So we have some options here. We could distribute across a few partition key values. We could choose to land it on a single partition key values, or we could distribute it across many partition key values. If we landed it on a single partition key value, that one single partition is going to get hot, right?
Yep. Across a few, that's going to help a little bit, but that doesn't sound right to me.
Yeah, so you're going to want to distribute it across as many of your physical partitions as you can, so that your write workload is evenly distributed at the moment in time. Remember that it's that moment in time that counts.
Yep. All right. Let's get moving because we're kind of running short on time here, I think. And what we're going to do is we're going to talk about modeling our small lookup tables. So in our products tables, we've got product category and product tag. And these are tables that are used as reference. So you look up the values within them and then you use them. And they have a one-to-many relationship to our product table here. So let's go and model these guys. So for the categories table here, next slide, we're going to model this with its ID, and then we'll use the name column as the property. And then we're going to put this thing in its own container, and we'll call that product category. Next, we need to choose a partition key for this. So we'll look at the access patterns for this. We need to create a product category. We need to edit a product category. we also need to list all the product categories. Now, we're not going to create or edit product categories very often. So listing the product categories is going to be the operation we run the most. And to do that, we'll use this, this query, select star from C. Now, one of the things that you may have noticed is that this would be a cross-partition query. There's no filter predicate. There's no where clause on this thing. So how do we possibly design this thing so that it's going to run as a single partition? Well, let's be honest here. This table or this container is never going to grow to 20 gigabytes in size. That's an insane amount of data for just listing product categories.
So it could all fit in a single logical partition, right?
Yeah, I mean, it'll easily fit within a single logical partition. But I'm going to make a change here, and I'm going to do something that's going to look a little different here. What I'm going to do is I'm going to add a new property. We're going to call this a type property, and it's functionally a discriminator property. And I'm going to give it a constant value. For product category, I'm going to put in the value category and have that for every single document that's a product category within my database. So now I'm going to have this new query, select star from C, where C.type equals category. Now I've got a way to have all of my product category data on the same logical partition. Now, I realize this looks a little weird. Well, let's do this. Let me do product tag, and then maybe I can explain this a little better. So here I'm going to do product tag. This is functionally the same as product category. I'm going to create a tag, edit a tag, and list all tags. So I'm going to do the same thing here. I'm going to create this discriminator property called type, and I'm going to give it a constant value of tag. So now I'm going to use this query, select star from C, where C.type equals tag. And I'm going to use that as my model, and I'm going to use type as my partition key for this container.
So I could put both of them in the same container then?
Well, that's the whole point, right? Is now that I have the same partition key for this data, I can now put it in the same container. And this is kind of the cool thing with Cosmos DB is that I can store different types of data, different entities in the same container, so long as they share the same partition key. This is going to give me much better storage efficiency because then I can only have to provision one container, and I could probably do it for like 400 RU, so the lowest amount of throughput I would need. And I can put all kinds of different types of data in here. I could put my category, I could put my type, I could put anything else where I'm going to partition it by that type property and use that to store all of my reference data. And I'm going to typically probably query this when the application starts and then cache this all up. And then not bother using it later. The other thing I could do with this as well, and we cover this in the second module for this talk, which, by the way, we'll have a link for this later, but we're going to do another Learn Live in December 7th that's going to talk about this. But we can use something called change feed to manage the referential integrity for all of this reference data that's stored here into any of the other tables where this data is denormalized. So like in our product table or product container, we're going to embed things like the category name and the tag names. If we ever change one of those things, like change a category name, we can use change feed to pick up that change and then propagate all those changes into the product container. So you get a lot of benefits, both on the storage efficiency as well as being able to maintain referential integrity between these things.
So let's have a quick look at what that looks like in practice, Mark.
Yep.
Let's go back to this database that we had earlier. And here we've got a version that's modeled slightly differently. We have this product meta container now. And within that, what we'll see here is that we have multiple different values for our partition key, where it's tag or category. And if I have a look at the actual queries, if I run a query, I can run exactly those queries that you had earlier there, where we go and select out just the data that we want. So if I'm looking just for category, I can just say where type equals category, and I can get that back. I could choose to find a specific item by just extending my where clause. But if I was looking for tag information, I could just pull back the tag information. And all of this lives in a single container here that we've got provisioned throughput for, completely separately controllable.
Yep. Very cool. I think are we due for another knowledge check?
We are due for another knowledge check. If I can find the slides. There we go.
All right. Let me read.
Let's do this. What is good design pattern when you're modeling small lookup tables in a NoSQL database with small amounts of data?
Let's see. So some options here. Let's start from the bottom up. We could put each entity into its own container. That sounds terribly relational to me, and not the pattern we want to use. Option B, we could group only those entities that have the same schema into the same containers and others into different containers. That also doesn't sound right to me, Gary, because Cosmos DB is schema agnostic. The only thing that matters is that they have the same partition key. So I think the answer is going to be A, which is put all entities in the same container and then use the discriminator property, which is the partition key, by the way, to distinguish between them.
Yep. There we go. Option A. When modeling your small lookup tables using a discriminator property like we just described, means that adding a new property with what kind of value? What is the value that we assign to that discriminator property?
Well, let's see. So you've got some choices here. We could go with an incremental value for each new document. That sounds terribly awful, I should say. Incremental value for each new document. So they'd each have their different, they'd each be in a different logical partition?
Yeah, and a random value for each new document has got the same problem. How would I know what I'm looking up, right?
I don't know. It's a guess. It's meant to challenge you, Gary.
So I think this one is by process of elimination. If you didn't even understand anything else, the same value for each entity.
I love these questions. We're meant to set you up for success, right?
So that wraps it up for the module today.
Yep, add some questions in there. I think we got a little bit of time. But let's go over kind of what we learned today. So we talked about kind of what are the differences between relational databases and NoSQL databases. And I think we uncovered quite a bit here and how these databases are different and the needs that these databases serve and why you would use one versus using another. We also talked about why access patterns are so important when modeling data. Not just to modeling the data, but also in choosing a partition key, understanding the access patterns to that data, and also the concurrency of that is so super critical. And just being able to measure, you have to measure these types of applications, these databases under load to understand what is the cost going to be so that you can design this thing to provide you kind of the lowest TCO for your solution. We talked about when to embed data versus when referencing it, and how the access patterns, again, whether data is read or updated separately or together, whether it's a one-to-one, one-to-few, one-to-many, whether that's bounded or unbounded in terms of one-to-many, all of those things matter in terms of embedding versus referencing the data. Choosing the partition key, so super important. That's the key to scalability within a database like Cosmos DB. You cannot scale if you don't choose a partition key that's going to allow you to do it, and try to avoid things like a hot partition on storage or a hot partition on request or compute. And then finally, we talked about modeling reference data and lookup data and how the kind of the schema agnostic nature of Cosmos DB makes that possible, and how that can provide additional efficiencies to your data model and your design within there, and how you can do really cool things when you have data that shares the same partition key, but is completely different schema, completely different design. Anything else? Did I miss anything? Oh, we have another question in here, Gary.
Oh, great.
Okay, from Hitesh. Having a type property is not suitable when a particular type can reach 20 gigabytes of data limit after 5 years. Do you archive the data after a few years? Well, let's be clear. So the reference or lookup data is not operational data. So this is suitable when you're looking at reference data, right? Like product category. The operational data or the transactional data is different. And that, like, I guess you could consider, like, say, in the second module, in the advanced one, we also have a container customer where we store one customer object and then put all the sales order data in there. So yes, there's an example where you'd have operational data. Yeah, Gary's going to show the model here.
So here we have customer, right? And in this scenario, we have a customer record, pretty much like the one that we had before.
Yep.
But if I ran a query against this customer, so if I went and had a look, and you can see there's a type attribute here associated with this customer now, which we didn't have before. If I ran a query against this and I said, where oops, if my typing fingers are done.
I'll let Gary type that query in. But the answer to your question, Hitesh, is yes. In scenarios like that, where you're storing transactional data and using a discriminator property like a type, like we do in our customer container in the final version of our database design, you would archive that data. And in fact, if you go to many e-commerce sites and you start scrolling back through history of orders, in many cases, you either have to wait for that data to show up, because in the back end, they're probably going into an archive to look up that data, or there's some other mechanism to getting at that data. Or in many cases, they may just say, hey, sorry, can't give it to you. So that's exactly what you do, is you would TTL that data off. And you can easily do that with something like TTL property that you've got within Cosmos DB. You could also do a double write for that data so that it's always stored in, say, blob storage, and then you TTL it off. So you don't have to do anything further on that. So yes, you could do that. You could also change feed it into another container using a different partition key. That partition key could be a combination of your customer ID and maybe date, like year or something like that. So I've seen e-commerce applications where it says, tell me what year you want to go look for that data. That's likely, if they're using a NoSQL database to store that data, that's likely how they're using it. But I'm guessing they're putting it into some kind of blob storage, and the year is going to help it find which blob container or similar type of function to go find that data. So yes, great question, sir.
Here, if we have a look at this customer record that we were talking about earlier, where we've modeled it now inclusive of type, the partition key that we're choosing is customer ID. If I query this data, what we'll see now is I can actually get back both the customer details and their sales order details, because we're using the same partition key value, the customer ID, for both of these sets of data. So the type is not just for those small scenarios. It's also useful where we want to combine data that's distributed on the same partition key across multiple partitions in this way. And you get all of the scale that you wanted. So there's two approaches. One for small data sets where you're going to constrain it to a single partition and partition on that, and the other one where it'll actually scale across all of your partitions because you use a different partition key value.
Yep. By the way, one other advantage for using different entities into the same partition key and the same partition key value is you can now use them in transactions. So you can do transactions types on that data, and we show an example of that in our follow-up lab on this. Just a quick reminder that this session is recorded, so you can come back and look at that on demand later. We have another question follow-up here. What do you do if you have several partition keys that are equally good and each are used the same percentage of your queries? Well, I guess you could use, I don't know. I guess I would need something more concrete if you're asking which one to choose. That's kind of,
you're going to need to pick one. So like if all of them, if the evaluation works out that they're exactly the same, you're going to need to pick one. And that would be the preferential one that you would then use. The alternative, and we show this in the advanced module, is you could put that data in another container and partition it differently in that other container. Using change feed, you can replicate the data into another container, have a different partition key associated with that, and use that for those other queries where it's appropriate using for that other partition key, where it's more efficient to use that other partition key.
Got yet another question here. When I have a great deal of update operations on some part of the document, how is Cosmos DB optimized for this operation? Well, as I mentioned earlier, if you have highly asymmetric access patterns and you have high concurrency updates on a small number of properties in a document, you have to design that to be optimal for Cosmos DB. When you do an update on Cosmos DB, you're replacing the entire document. And if the document is quite large, this can be quite expensive. So if you want both efficiency in terms of throughput usage and also lower latency, the right approach is to shred that document and to split it into two documents. One that has a small number of properties that are updated with high concurrency, high frequency, and another one that's not updated as much or maybe at all. And then if you want to access the entire thing, you would write a query to get it. Otherwise, you can use point operations like updates to update it. You can also use our new partial document update or patch operation, which we just announced today as well. And if you go to our blog, you can learn about it. Another question, Gary, from Stan L. Is it a bad idea to use Orms, such as Entity Framework, to NoSQL databases like Cosmos DB? Well, here's what I'll say is I know lots of people like using Orms and love using Entity Framework. I think an Orm, and this
it makes it really easy to work with the data, right? So from a developer perspective, the efficiency is obviously there to work with the data in a nice, flexible way.
I think that Orms are great in that they help extract away some of the more complex things about a database. And I think they make more sense for relational databases than they do, say, for a document database like Cosmos. That said, Jeremy and the folks over in the EF team do a great job supporting Cosmos with lots of new updates, lots of new features. You know, I'll be honest, there are some rough patches there. It doesn't have kind of the full fidelity that you have with, say, Entity Framework over SQL. But we're working to try and make that better. I think if you use an Orm, however, you're always going through something to get ultimately to the database. So if your objective is to write super high performance applications, you're going to want to get low level, and you're going to want to go directly against our SDK.
You're going to want to write that code to optimize for that latency or for that reduced request unit cost associated with it.
Yep. Great question. Oh yeah, so lots of announcements today. How do I put this? I guess I can try and share. Let me get rid of this thing here. Let's talk about all the announcements we've got. That's in the wrong thing. Where are you? All right, so why did you keep loading in the wrong thing? All right, you want to show my screen? I want to share some of the updates that we've got today. Oh, hold on. I need to share. This is really... okay, here we go. So we announced a ton of new stuff today. We've got partial document updates. This is like #1 on user voice, like over 5,000 votes. It's been there for 5-6 years. We now finally have support for that. This is a super cool feature. You've got to go check it out. I think we're going to do more in-depth blog post, or we do have a more in-depth blog post on it. Azure cost savings recommendations. This is really great. Show you where you're spending your money when you're using Cosmos. We have the ability to be able to set a maximum throughput at the account level. So if you say create a free account, you can say max throughput at 400, and it'll never go above that.
And to manage those developers in your department as well that keep wanting to create new provision throughput as well.
Yeah, that's right. This is made for that one guy that keeps creating a container with 1 million RU. So now you can stop him from doing that. A new connector. Oh, custom partitioning for Azure Synapse Link. This is also very cool to help make more efficient queries for your data when you're doing analytics.
So you can optimize your queries on the
analytics
analytical
side.
Queries compared to what you're optimizing for on the transactional side.
Yep. A new connector for logic apps. This is out now in a preview. I know there's a big update coming later as well, but go and check this out. Brand new connector for the logic apps within there.
Super exciting, that.
Very cool. Server-side retries for our Cassandra API. So this is really helpful for users that are trying to ingest large amounts of data and keep getting tripped up with having to write really complex retry logic because we throw 429s rather than building queue depth for requests, like you would see if you were doing this, like say hosted on a VM or something like that.
We've had it for Mongo for a little while now, and the customers really saw benefit there.
Same reason,
nice
right?
to have it for Cassandra.
That's right. Most people are used to using Mongo on a VM, and when they ingest large amounts of data, VMs will queue those requests up rather than just rejecting them when they get to a certain point. But in a resource-governed service like ours, we rate limit you, right? We don't just build up queue depth. Server-side retries corrects that and makes that much smoother now. Apache managed instance or Azure managed instance for Apache Cassandra. now GA. This is also, we're really super excited about this. This really provides customers who are running Apache Cassandra on premises or on VMs a way to do this in a more managed environment. And if they want to go eventually fully Cassandra API and be completely fully managed, they can, or they can just migrate and start migrating their workloads over to a fully managed instance, if you will, running Apache, full native Apache. So very cool. Let's talk, Gary, back to you. I want to show that last screen for with the URL for the Ignites in there. So can we get back over to Gary's screen there? Yeah.
So this is just a reminder to go through the module yourself. Today's session was a quick walk through this module, but you'll get real good hands-on experience if you step through it and do the exercises and explore the data. Inside that code that's in there, Mark showed a little hint at what's going on in there. There's a lot of stuff in there that you could explore on your own as well.
You know, you could go and clone that into your own repo as well. And I think you could nearly set it up entirely. I think it's a bit of tricky if you're going to run that shell script because it kind of assumes there's just a single resource group in the subscription. So you may want to.
If you replace that, if you have a look at that shell script, you can just replace the resource group with a known resource group in your subscription, and it runs perfectly fine. I actually set one up as a backup for today, just in case things went wrong.
Cloud Shell
using exactly that approach.
Cloud Shell was acting a little weird yesterday. There's lots of great stuff in that repo, and not to mention there's the V2, the advanced modeling, which Gary now has up on the screen. And the Learn guys are going to run a Learn Live session on that with a couple of great folks, Alex Mang and Glenn Colpert. And they're going to walk you through the second module for this kind of two-part series, if you will.
That's coming up next week on the 7th.
Not next week. It's next month.
Next month. Yep, next month. Sorry.
You're in a time warp there, buddy. And that'll be 10 a.m. to 11:30 a.m. Central European time. And of course, that'll be available on demand as well. And certainly go and check that out for sure. That's going to be great. That's a really fun module because you'll get to see how we use change feed in there. You'll get to see all those advanced pieces in there. And you'll get to see what the final model looks like where we take what is it? Is it 11 tables, Gary, that we started with relational?
I think we start with 9, and at 9? The end we end up with 5, right? I think that's what it is. It's
cool, right? So go and watch that.
We gave you a little taste in some of those demos.
We gave you a little teaser there, showing you the code that's available in there. And plus, if you're just new to Cosmos, that project in there has great API samples on how to using Cosmos in there, using kind of all the point operations, whether it's create, update, delete. It shows transactional batch.
And the change feed.
And change feed, right? So all the basics, all the goodies that you need, plus all the knowledge you get to model and partition your data so that you're running, as efficiently and as fast as you can using Cosmos as a database. So anything else?
Just a reminder to never stop learning. This is part of the Learn Live series, and there will be more of them. Post-Ignite, all of these sessions are recorded and will be available for you to review at that stage.
Yep, and then be sure to visit the Learn collection for this session, and also sign up and complete the Cloud Skills Challenge now and afterwards as well, right? Ignite's never over, right? It's a feeling, not an event.
And lastly, any other outstanding questions that we haven't answered, Mark?
I don't see any. I haven't seen any come across the wire, so I think we've answered everyone's question.
Great, and we dead on time.
That's fantastic. I think, Gary, thank you so much for joining me today, and thank you, everyone, for joining us for our Learn Live session. We hope you really enjoyed it. We hope you got some great knowledge out of this and have the confidence to go and start designing and building using Cosmos DB.
Thanks, Mark. Thanks, everyone.
Thank you.